Today we're going to be learning arithmetic. We're going to be covering the basic building blocks for everything that you're going to need to answer math test questions. My name is Josie and we're going to be going through these concepts one by one together. The first topic that we're going to cover is integers. Here's what you need to know about integers. Integers are going to be whole numbers, the numbers that you count with. Remember that integers do include negative numbers and zero. Many test questions are going to further limit the way that you think and use integers by adding other descriptor words, such as positive integers. If a test question says that you need to use a positive integer, you're going to be looking at integers that are greater than 0. So for example, 1, 2, 3, 4, etc. A negative integer, similarly, are going to be integers less than 0. So for example, -1, -2. You may see a test question that asks you to consider even or odd integers. An even integer is divisible by 2. So for example, -4, -2, 0, and 2. Notice that that list included negative values. So you could be asked for an even integer that is negative. An odd integer is going to be those integers that are not divisible by 2. So for example, -3, -1, 1, 5, etc. Prime integers are going to be integers that are only divisible by 1 and itself. For example, 2, 3, 5, etc. Remember that prime integers do need to be greater than 1. Finally, remember that 0 is going to be the only non-negative, non-positive integer. So don't forget about 0 when you're doing questions that require you to look at integers. Let's go ahead and take a look at an example. All right, if you're given the set of numbers 3, -26, the square root of 2, 1/4, 0, and pi, which of those numbers are integers? Okay, we've got 3 integers in that list. 3, -26, and 0. Notice that we did have a negative integer and we did have a 0. Now, which of the numbers are positive? Okay, now we have a few more numbers. 3, square root of 2, 1/4, and pi. Notice that I didn't ask for positive integers, I asked for positive numbers. So we included the square root of 2, 1/4, and pi. Now, which of the numbers are odd? There's only going to be one number in this list that's odd, and that's the number 3. If you're dealing with a non-integer value, it's impossible to determine whether it's odd or even. Finally, which of this set of numbers is prime? Again, we only have one prime number, and that's the number 3. Let's look at a definition before we go to the exercises. You may see in your questions the term digits. What you want to think about with that word is that digits are describing the numbers that make up larger numbers. They're basically the math alphabet. So just as we group and order letters to form different words, we can also group and order different digits to form different numbers. So for example, the number 128 is made up of 3 digits, 1, 2, and 8. We could take those 3 digits and rearrange them to make a new number, such as 281 or 812. Keep that definition in mind as you do the 6 integer exercises. I'll give you a couple of minutes to try those exercises out, and when you're finished, we'll go over the answers and then we'll review a few of those questions together. Okay, stop working. Now check your answer. Now that you've checked your answers, let's go through a couple of these examples together. The first one, number 1, asks us which of the digits in the number 27,536 are even. Remember, because this question asks us about digits, we don't really need to concern ourselves with the number 27,536. Rather, we want to look at the individual numbers that make up that larger number. So we have 5 digits to consider: 2, 7, 5, 3, and 6. Out of those 5 digits, how many of them are even? Well, looking at that list, we only have 2 even numbers, 2 and 6. So the answer to this question is just that, number 2 and number 6. Now let's take a look at number 3. This question asks us to arrange the following numbers in numerical order: 14, negative 23, 0, negative 30, and 6. Remember that when we want to arrange a set of numbers in numerical order, we want to start with the smallest number first. Since we have negative numbers in this list, we want to deal with the negative number that has the largest absolute value. In this case, it would be negative 30. The next largest would be negative 23, then 0, and now that we've reached 0, we can go with our positive integers, 6 and then 14. Finally, let's take a look at number 6. This question asks us to identify the smallest prime number. Remember that prime numbers are numbers that are only divisible by 1 in itself, and prime numbers must be greater than 1. So the smallest prime number is 2. This is a very special prime number. You're going to want to remember it because it's the only even prime number. Now that we've gone through a couple of exercises, let's try a test question. Number 7 asks us, if 3x plus 10 represents an odd integer, which of the following represents the next largest odd integer? Now, before we look at the answer choices, I want you to think about actual numbers. Let's say we're thinking about the number 3. When you have 3, how do you get to number 5? What do you need to do to 3 in order to get to 5, which is the next largest odd integer? All you would need to do is add 2. So, going back to our test question, if 3x plus 10 is an odd integer, all we need to do is add 2 to that expression in order to generate the next largest odd number. So, 3x plus 10 plus 2 is going to give us 3x plus 12. Notice when you look at the 5 answer choices, none of the 5 answer choices say 3x plus 12. This is because test makers like to change the format of the answer choices so that it doesn't match exactly what you may have written on your scratch paper. The good news is that all we need to do is factor, in this case factor out of 3, in order to make it look exactly like one of those answer choices. When you factor out of 3, you get 3 on the outside of the parentheses times x plus 4, which matches with answer choice C. The next topic we're going to cover is factors, multiples, and remainders. These are probably topics that you haven't looked at in a long time, so make sure to review these definitions and concepts. The first one you're going to want to know is that factors are positive integers that divide evenly into a number. Another way to think about that is that factors are going to be the small numbers that go into the bigger numbers evenly. The next term, multiples. Multiples are going to be the integers that are divisible by another integer. They're going to be the numbers that we generate from smaller numbers. Now, a note on both factors and multiples: any given integer is going to have a finite set of factors. There's only so many integers that will divide cleanly into another integer. Multiples, on the other hand, are an infinite list. There's no limit to the number of numbers that we can generate when we multiply 2 integers by each other. Next, we have the concept of remainders. Remainders are basically just the value of whatever's left over in a division problem. It's always going to be smaller than the number that we're dividing by. You've likely worked with remainders when you've done long division problems, but we get used to expressing remainders as a fraction or a decimal. On test day, you may see questions that ask you to express remainders as integer values. So we'll go over some exercises so that you learn how to do that. Let's take a look at an example. First example asks us to determine the greatest common factor of 12 and 18. The first step is to determine what are the factors of 12. Remember, factors of 12 are going to be those integers that 12 is divisible by. It's often easier to think about factors in their pairs. So for example, what two numbers when multiplied together give you a product of 12? We have 1 and 12, 2 and 6, and then 3 and 4. And that's our list of factors of the number 12. Now let's determine the factors of 18. Again, what two numbers when multiplied together give you a product of 18? We have 18 and 1, 2 and 9, and 3 and 6. Now, when you take a look at the lists for both the factors of 12 and the factors of 18, you'll see that they have multiple numbers in common. But this example is asking us to find the greatest common factor. So we want to find the largest integer that's in common on both lists. That number is 6. That's going to be the greatest common factor of 12 and 18. Now let's go ahead and look at an example that teaches you how to calculate the remainder. First example asks us to calculate the remainder when 34 is divided by 3. Our first step is to determine the quotient. So what we're going to do is put 34 inside a division box and put the 3 on the outside. Now we need to determine how many times does 3 divide into 34. And you want to break this up by digit. So first ask yourself, how many times does 3 go into 3? That's just one time. So write a 1 above the 3, and then multiply 1 times 3 to see if there's anything left over. 1 times 3 is 3. There's nothing left over, so we can carry the 4 from the 34 down. Now, the next step is to determine how many times 3 goes into 4. 3 goes into 4 one time as well, but this time when you multiply 1 times 3, we get 3, leaving us with 1 left over. That is your remainder of 1. Now let's go ahead and take a look at some exercises that test your knowledge of factors, multiples, and remainders. Take a few moments, and when you're finished, we'll review these answers and go through a couple of examples together. put down your pen. Now go ahead and check your answers. Now that you've looked at your answers, let's go ahead and take a look at a few of these exercises together. The first one, number 1, asks us to find the factors of the following numbers. Number 1 gives us the number 36. Just like in the previous examples, we want to determine what is the set of numbers that 36 is divisible by. We have 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6, because 6 times itself is equal to 36. Now let's go ahead and take a look at example number 5. This question asks us to list the first 5 multiples of the following numbers. Number 5 gives us the number 6. In order to generate the first 5 multiples of the number 6, what we want to do is multiply 6 by every integer starting with 1. So the first multiple is going to be 6 times 1, which is 6. The next multiple will be 6 times 2, which is 12. The third multiple will be 6 times 3, which is 18. The fourth will be 6 times 4, which is 24. And the fifth will be 6 times 5, or 30. So the first 5 multiples of the number 6 are 6, 12, 18, 24, and 30. Now let's go ahead and take a look at number 9. These questions are asking us to calculate the remainders. Number 9 asks us to divide 68 by 5. So we're going to put 68 under the division bar and put 5 on the outside. And again, think about each integer one at a time. How many times does 5 go into 6? It goes in once. 1 times 5 is 5, so there's 1 left over. We carry the 8 down and then ask ourselves, how many times does 5 go into 18? 5 goes into 18 3 times. 3 times 5 is 15, which means that we have 3 left over and there's no more numbers to carry down, which means that 3 is our remainder. Now let's take a look at another example, number 10. This question asks us to divide 93 by 4. Again, looking at each integer one at a time, 4 goes into 9 2 times. 2 times 4 is 8, and that leaves us with a leftover of 1. We carry the 3 down and then ask ourselves, how many times does 4 go into 13? 4 goes into 13 3 times. 3 times 4 is 12, which means that we have a remainder of 1. Now that we've gone through and done a few exercises, let's try a test question. Number 13 says, which of the following is not a factor of 168? Now, we could take each one of those 5 answer choices and do the long division to see which integers do divide evenly into 168 and which integer does not. But there's a faster way. Anytime you see a large number for which you cannot easily generate a list of factors, what you're going to want to think about is prime factors. Every single non-prime number can be broken down into a series or a product of prime factors. All you need to do to create a factor tree is to start breaking 168 down into its factors and continue breaking those factors down until you have only prime numbers. So let's go ahead and start with the number 2. 2 divides evenly into 168. And what times 2 equals 168? It's 84. So our factor tree now has 2 and 84. 2 is already a prime number, so we don't need to break that down any further. 84, however, can be broken down into 2 and 42. Again, we don't need to break down 2 any further, but 42 can be broken down into 2 and 21. 21 can be further broken down into 3 and 7. Now we have only prime factors, so let's go ahead and list them. Another way of expressing 168 is 2 times 2 times 2 times 3 times 7, or 2 to the third times 3 times 7. Now, in order for an integer to be a factor of 168, it needs to contain some combination of those three factors, 2, 3, and 7. The one thing to pay attention to is that the factors cannot exceed the limits set by those prime factors, which means that at most we could only have 3 2s, 1 3, and 1 7. If we have more than that, the number is not going to be a factor. Let's go ahead and take a look at our 5 answer choices now. Answer choice A, 21. Well, 21 is just the same as 3 times 7. That doesn't exceed any of the limits on our prime factors, so 21 is going to be a factor of 168. Remember that we're looking for an integer that is not a factor, so let's cross out answer choice A. Answer choice B, 24. 24 is just going to be 2 times 2 times 2 times 3, or 2 to the third times 3. Again, take a look at your list of prime factors for 168. We've got a 2, we've got a 3, and we haven't exceeded the limits at all. So answer choice B is also going to be a factor, and we can cross it off. Answer choice C gives us the number 28. 28 is going to be 2 squared times 7. Again, we haven't exceeded the limits. That's going to be a factor as well. Now, let's take a look at letter D. We have the number 32. 32 can be broken down into a series of 2's, but let's count how many there are. 32 is going to be equal to 2 to the 5th power. 2 is an acceptable prime factor, but as you can see from our limits, we can only at most have 3 2's. So answer choice D is going to be our correct answer. 32 is not a factor of 168. Let's just double check answer choice E, 42. 42 is going to be the product of 7 times 2 times 3. That's just fine. All of those factors are included and we haven't exceeded the limits. So our correct answer here is letter D. The next topic that we're going to talk about is divisibility. You can use factors and prime factors to determine whether or not a number is divisible, but another way is to use divisibility rules. We're going to go through these rules because they determine whether or not a number is divisible by a particular integer. And then we'll go ahead and try this on a couple of different examples. A number is going to be divisible by the integer 2 if that number is even. It's going to be divisible by 3 if the sum of the digits is divisible by 3. It's going to be divisible by 4 if the last 2 digits are divisible by 4. It's going to be divisible by 5 if the last digit is 0 or 5. It's going to be divisible by 6 if the number is divisible by both 2 and 3. By 9 if the sum of the digits is divisible by 9. And by 10 if the last digit is 0. So let's try this on an actual example. Determine if 216 is divisible by the following. Is it divisible by 2? Remember that if it is divisible by 2, then the number needs to be even. 216 is even, so yes, 216 is divisible by 2. Is 216 divisible by 3? If yes, then the sum of the digits of 216 must add up to a number that is divisible by 3. Let's take a look at those digits, 2, 1, and 6. When you add those together, you get the number 9, which is divisible by 3, which means that 216 is also divisible by 3. Is 216 divisible by 4? If it is, the last 2 digits should be divisible by 4. The last 2 digits of 216 are 16, which is divisible by 4, which means that yes, 216 is divisible by 4. 216 is not divisible by 5, however, because the last digit of 216 is not 0 or 5. Is 216 divisible by 6? It is if it's also divisible by both 2 and 3. Taking a look at your notes, we can see that 216 is divisible by both 2 and 3, so by definition, according to the divisibility rules, it's also divisible by 6. 216 will be divisible by 9 if the sum of its digits add up to a number that's divisible by 9. Again, add 2 plus 1 plus 6, which gives you 9, which is divisible by 9, which means that 216 is divisible by 9. Finally, is 216 divisible by 10? No, the last digit is not 0, so 216 is not going to be divisible by 10. Before we move on, you may have wondered why 7 and 8 weren't considered. The reason for that is because there is no special divisibility rules that govern 7 and 8. If you want to determine if 216 is divisible by 7 or 8, you're going to have to do the long division. It is divisible by 8, but not by 7. Now, I'm going to give you a few minutes to take a look at a few divisibility exercises. Take a few moments, go through each of the exercises, and when you come back, we will go through the answers and evaluate some of these examples together. Time's up. Now go ahead and correct your answers. let's go ahead and go through a few of these exercises together. Number 1 asks us, which of the following numbers is divisible by 3? And we have a list: 241, 1,662, 4,915, 3,131. Remember that in order for a number to be divisible by 3, the sum of each of its digits needs to also be divisible by 3. So let's go through each of these 4 numbers together. The number 241 is made up of the digits 2, 4, and 1. When we add up those 3 digits, we get the number 7, which is not divisible by 3, which means that 241 is also not divisible by 3. Our next number, 1,662, is made up of integers 1, 6, 6, and 2. When you add those 4 integers, we get the number 15. 15 is divisible by 3, so 1,662 is divisible by 3. Let's take a look at the next number, 4,915. 4 plus 9 plus 1 plus 5 is equal to 19. 19 is not divisible by 3, which means that that number is also not divisible by 3. Finally, we have 3,131. Add the digits, 3 plus 1 plus 3 plus 1, and we get the value of 8, which is not divisible by 3, which means that 3,131 is not divisible by 3. Let's go through another example. Example number 2 asks us which of the following numbers is divisible by 4, and we have the numbers 126, 324, 442, and 598. The divisibility rule for 4 dictates that the last 2 digits must be divisible by 4 in order for the number to be divisible by 4. So, looking at our first example, 126, 26 is not divisible by 4. So 126 can't be divisible by 4. Our next example, 324. The last 2 digits are 24. 24 is divisible by 4, which means that 324 is also divisible by 4. 442. Our last 2 digits are 42. 42 is not divisible by 4, which means that 442 is not divisible by 4. Finally, we have 598. 98 is also not divisible by 4, which means that 598 is also not divisible. Now let's try a test question. Number 6 says, which of the following is a multiple of all 3 integers, 2, 3, and 5? With a question like this, you want to ask yourself, what needs to be true of this number in order for it to be a multiple of all 3 integers, 2, 3, and 5? Another way of saying that is that the correct answer is going to be divisible by all 3 of those integers. That's what we should look for. Let's start with the divisibility rules for 2. A number that's divisible by 2 must be an even integer. So taking a look at your list of 5 answer choices, that allows us to cross out answer choice A, 525, and answer choice C, 615. Now let's consider the divisibility rule for 3. In order for our answer to be divisible by 3, the sum of its digits must be divisible by 3. Let's look at the remaining answer choices that we have left. Answer choice B, 560. When we add those 3 digits, 5 plus 6 plus 0, we get 11. 11 is not divisible by 3, so we can cross out answer choice B. Take a look at D, 620. The sum of those digits is 6 plus 2 plus 0, which equals 8. Again, 8 is not divisible by 3, so we can eliminate choice D. Answer choice E is the only answer that we have left. Let's go ahead and check it. 660. When you add up the digits, 6 plus 6 plus 0, we get 12, which is divisible by 3. Now, on test day, you would choose this answer choice and move on because it's the only answer choice left. But let's just go ahead and check to make sure that this answer choice is also divisible by 5. 660 does end in 0, and remember that the divisibility rule for 5 is that the number should end in 0 or 5. The next topic that we're going to look at is fractions. Fractions are going to be the result when we do the operation of division and don't get an integer result. For example, a fraction 1/2 represents the result of dividing 1 by 2. Now there's a couple of different ways that you're going to need to manipulate fractions in order to be able to perform operations. One of the things that you're going to need to learn how to do is reduce a fraction. In order to reduce a fraction, you're going to want to divide the numerator and the denominator by the same number. You also may be asked to convert a fraction into an equivalent fraction or into a decimal. In order to convert it into an equivalent fraction, you're going to just multiply the numerator and the denominator by the same number. These two actions, reducing a fraction and converting a fraction to an equivalent fraction, are going to be useful when you're adding and subtracting fractions and you need a common denominator. You may also need to convert a fraction into a decimal. In order to convert a fraction into a decimal, you're going to divide the numerator by the denominator. To convert a decimal into a fraction, you're going to move the decimal to the right until the number is an integer. Then you're going to set that integer over 10 times the number of places that you moved the decimal place to the right. Let's take a look at an example that asks us to convert the fraction 1/2 into an equivalent fraction with a denominator of 6. The numerator is going to be the top number of your fraction. The denominator is going to be the bottom number. So if you're trying to convert 1/2 into a fraction with a denominator of 6, you want to ask yourself, what do I need to multiply that bottom number by in order to get a denominator of 6? 2 times 3 is equal to 6. And because we multiply the denominator by 3, we also need to multiply the numerator, or the top number, by 3 as well. So the equivalent fraction would be 3/6. Now let's try reducing a fraction. The next example asks us to reduce the fraction 15/35 to its lowest terms. What you want to look for is what is the factor that is in common between 15 and 35 that we must divide both the numerator and the denominator by. Both 15 and 35 are divisible by 5. So if we divide the top, or the numerator, by 5, we get 3. If we divide the bottom number, or the denominator, by 5, we get 7. So our reduced fraction is going to be 3/7. Now let's take a few moments for you to complete the fraction exercises. After you're finished, we'll check your answers and go through a few of these examples together. Okay, now that you've had a chance to try those exercises, let's go ahead and check your answer. Okay, now that you've looked at the answers, let's go ahead and walk through a few of these exercises together. The first one asks us to convert the following fraction to a decimal. We have the number 1/3. In order to convert 1/3 to a decimal, we want to divide 3 into 1. Now, many of you will notice that 3 does not go into 1 any times. So the first number that you're going to put down in that long division problem is 0. When you multiply 0 times 3, you get 0. And now we need to move over to ask ourselves, how many times does 3 go into 10? 3 goes into 10 3 times. 3 times 3 is 9, and there's 1 left over. Now we're going to carry a 0. Again, we're asking ourselves, how many times does 3 go into 10? 3 goes into 10 3 times. 3 times 3 is 9, and again we have 1 left over. Anytime you notice this, that the exact same numbers are being generated and you're putting the exact same numbers on the top of your fraction problem, we're looking at a repeating decimal, a decimal that repeats indefinitely. You can stop when you've determined this pattern and just write a bar over the numbers that are repeating. So 1/3 converted into a decimal is 0.33 repeating with a bar over the 3. The next example asks us to convert 2/5 into a fraction. So again, we're going to put 2 under the fraction bar and divide 5 into 2. 5 goes into 2 0 times, so write down a 0 above the 2 and put down your decimal point. Now we want to ask ourselves, how many times does 5 go into 20? 5 goes into 20 4 times, and it goes in evenly. 5 times 4 is 20. So unlike the previous example that had a repeating decimal, this one does not. 2/5 is equal to 0.4. Now let's take a look at number 6. This question is asking us to convert the decimal into a fraction. Remember, the steps for doing so are to move your decimal point over to the right as many places as you need to in order to turn that decimal into a whole number. Then put that whole number over 1 times the number of zeros that you moved the decimal place over. So, number 6 gives us 0.45. We're going to move our decimal place over 2 places to give us 45. And because we moved it over 2 places, we're going to put 45 over 100, a 1 followed by 2 zeros. Now we can reduce 45 over 100. We learned how to do that. We need to find a factor that goes into both 45 and 100. That number is 5. When we divide 45 by 5, we get 9. And when we divide 100 by 5, we get 20. So our reduced fraction is 9 over 20. Now let's take a look at number 8. 2.25. Anytime you have a whole integer in front of the decimal, that's going to be in addition to the fraction. So let's go ahead and write down a 2. And now let's convert the decimal portion of that number into a fraction. Some of you may remember that 0.25 is equal to 1/4. But the other way of doing that is to move your decimal place over 2 places to the right to get you 25 over 100, which can then be reduced to 1/4. So 2.25 is equal to 2 1/4. Now let's go ahead and try a test question. Number 11 says 6 3/4 minus 6.32. Notice that there's no direction that tells you whether you should convert the fraction to a decimal or the decimal to a fraction. You might want to look at your answer choices to give you a hint about this one. All of the answer choices are expressed in decimal format. So that tells us that it's going to be a more efficient method to convert our above expression into all decimals. 6 3/4, again, 3/4 is probably a fraction that you know the decimal equivalent to. It's 0.75. So let's convert 6 3/4 to 6.75. subtract 6.32. All you need to be careful of here is that you line up your decimal points and then subtract column by column. 5 minus 2 is 3. 7 minus 3 is 4. Drop down your decimal point. 6 minus 6 is 0. Our correct answer is 0.43, or answer choice. So now that we've talked about how to reduce a fraction and how to create an equivalent fraction, let's talk about improper fractions and mixed fractions. Improper fractions are going to be fractions in which the numerator is greater than the denominator. Mixed fractions are going to be fractions that contain a whole number, like 1 7/8. For the most part, you're going to want to convert mixed fractions in order to be able to add, subtract, multiply, and divide them. So let's go over the steps for converting a mixed fraction. Step number 1, multiply the whole number by the denominator. Then, step number 2 is to add the numerator. Step number 3 is to take that total and put it over the denominator. Let's try an example. Take the mixed fraction 1 7/8. Step 1 is to multiply that whole number by the denominator. So 1 times 8 is equal to 8. Then take that value and add in the numerator. 8 plus 7 is going to be 15. Finally, step 3 is to take that total, 15, and put it over the original denominator, which is 8. So 1 7/8 is equal to 15 over 8. Now, there's a couple of things that you need to know about performing fraction operations. When you add and subtract a fraction, all of the fractions involved must have a common denominator. When at all possible, make sure to determine the least common multiple of the denominators so that you're using numbers that are easy to perform calculations with. When you're multiplying a fraction, you don't need to worry about common denominators. Just multiply the numerators and the denominators separately. When you divide fractions, what you're going to really end up doing is multiplying the first fraction by the reciprocal of the second fraction. So, for example, 1/2 divided by 3/4 will become 1/2 times 4 over 3. Let's go ahead and try a few examples. First example asks us to determine the sum of the following expression, 3 over 5 plus 2 over 3. Our first step is going to be to find the lowest common multiple. If you take a look at the two denominators, we have 5 and 3. The lowest common multiple is going to be 15. Now that we know that the lowest common multiple is 15, we're going to need to calculate the equivalent fractions. So, our first fraction is 3 over 5. What do we need to multiply 5 by in order to get a 15 in the denominator? 5 times 3 is equal to 15. So we're going to need to multiply the bottom by 3. And because we multiplied the denominator by 3, we also need to multiply the numerator by 3. So 3 times 3 is equal to 9. 5 times 3 is equal to 15. Our new fraction is 9 over 15. Let's do the same process for our second fraction. Our second fraction is 2/3. So we need to ask ourselves, what times 3 is going to equal 15 in the denominator? That's going to be 5. So we're going to multiply the top and the bottom by 5 over 5. 2 times 5 is 10. 3 times 5 is 15. Now that we have two fractions, 9 over 15 and 10 over 15, that have the same denominator, we can now perform the addition problem. Add your numerators only. 9 plus 10 is equal to 19. And then put that over the same denominator, 15. So the sum of 3 over 5 plus 2 over 3 is equal to 19 over 15. Now let's go ahead and try some exercises. Take some time to try the following expressions, and when you're finished, we'll check your answers and go through a few examples. Okay, put down your pens and check your answers. You've taken a look at the answers. Let's go ahead and go through a few of those examples together. Let's start by going over example number 2. This question asks us to add 12 over 25 plus 13 over 5. Now remember that when you're adding fractions, you need to have a common denominator. But the good news is that in this case, 12 over 25 already has the lowest common multiple as our denominator. All we have to do is convert 13 over 5 into a fraction that has 25 as its denominator. We can accomplish that by multiplying both the top and the bottom by 5, giving us a new fraction of 65 over 25. Now that we have a common denominator, all we need to do is add the numerators only. So 12 plus 65 gives us 77, and then we keep the same denominator. So our answer is 77 over 25. Let's take a look at example number 8. This example contains only decimal numbers, and we're supposed to solve the following expression: 0.21 plus 0.946 plus 1.324. The trick here is to line up your decimal points and then add each number in its column from right to left. So in our first column, on the right-hand side, we have 0 plus 6 plus 4, which is 10. Write down the 0 and carry the 1. We then have 2 plus 4 plus 1 plus that carryover 1, which gives us 8. Our next column is 3 plus 9 plus 2, which is 14. Put down your 4 and carry the 1. And then our last column is going to be 1 plus the carryover 1, so 2. Final answer is going to be 2.48. Now that you've tried some examples, let's go ahead and take a look at a test question. Number 11 tells us to multiply 7 over 5 times the quantity of 3 over 7 minus 2 over 5. Note that we need to perform the subtraction problem inside the parentheses before we multiply by 7 over 5. And, as with addition, subtraction questions require a common denominator. Common denominator between 7 and 5 is 35. So to convert our first fraction, we're going to multiply by 5 over 5, giving us 15 over 35. Our next fraction needs to be multiplied by 7 over 7, giving us 14 over 35. So our new fractions inside the parentheses are 15 over 35 minus 14 over 35. Subtract the numerators only to give us 1 over 35. Now that we've completed the subtraction problem, we can multiply 1 over 35 times 7 over 5. Now, when you're multiplying fractions, you don't need to have a common denominator, but it is useful to cancel diagonally if you can in order to make your calculations easier. In this case, 7 goes into 35 5 times. So the 7 cancels out, the 35 changes to 5, and our multiplication problem becomes 1 times 1 in our numerator and 5 times 5 in our denominator, giving us a value of 1 over 25, or answer choice C. The next topic that we're going to take a look at is ratios. A ratio represents the proportional relationship between quantities or numbers. If you're given the number of each item, then you can determine the ratio, or their relationship to each other. The values of a ratio are going to represent the smallest possible quantity of each item. But if you're just given a ratio, those are only one possible set of numbers that you could have for each item. You could also have any multiple of each item. Ratios are going to be expressed in a variety of different ways on test day. Most commonly, they're going to be written with a fraction bar, so x over y. You could see them with a colon, x colon y, or just written out in a word problem in English, the ratio of x to y. Now, when you're working with ratios, you're going to want to make sure that you keep track of which values are real quantities and which values are relationship quantities. So for example, if the ratio of apples to oranges is 2 to 3, 2 to 3 is a relationship that doesn't dictate the actual number of apples and the actual number of oranges. You could have 2 apples and 3 oranges, or you could have 4 apples and 6 oranges. Let's try an example. Here's what we have. A classroom has a ratio of 4 girls to 5 boys. If we want to determine the ratio of girls to students, we need to re-express the above ratio. The minimum number of girls is going to be 4. We determine the minimum number of total students by adding 4 to 5. 4 girls plus 5 boys. So our ratio of girls to students is going to be 4 over 9. What this tells us is that the smallest number of girls is going to be 4, and the smallest number of total students is going to be 9. But what if a question stem gives us more information? What if it does give us an actual value? Let's take a look at the next example. Using the same ratio, if there are 36 students in the class, determine the number of girls in the class. First, we want to consider what is the ratio of girls to students. It's 4 to 9. Now we need to apply the ratio formula, or set it equal to the relationship between the actual numbers. We don't know the actual number of girls. That's going to be X. We do know the total number of students, which in this case is 36. Now all we need to do is solve our equation for X. You could cross multiply, or you could just ask yourself, what times 9 equals 36 in our denominator? 9 times 4 equals 36. So we're going to need to multiply our top number by that same factor. 4 times 4 is 16, which means that if there are 36 students in the class, there are going to be 16 girls. Now let's go ahead and take a look at a few ratio exercises. I'm going to give you a few minutes. Try these exercises on your own. Then we'll check your answers and go through a few of them together. Okay, time's up. Now check your answer. Okay, now that you've looked at those answers, let's go ahead and go through a few of these exercises. Number 1 asks us to reduce the ratio of 8 to 128 into its lowest terms. Now, remember, ratios could be expressed in a variety of different ways. This is one way, 8 colon 128. Another way is as a fraction, 8 over 128. When you see it in fraction format, reducing it is a skill that we learned when we did our fraction exercises. You just have to divide the top and the bottom by the same factor until we have the lowest number possible. Both 8 and 128 are divisible by 8. 8 divided by 8 is 1, that's our numerator. 128 divided by 8 is 16, that's our denominator. So our new ratio, expressed in lowest terms, is 1 over 16 or 1 colon 16. The next example that we're going to take a look at is number 4. A bag contains red and blue balls. If there are 10 red and 12 blue balls, what is the ratio of red to blue balls? Since we know the actual values, all we need to do is express those actual values in the correct order in order to determine the ratio. So, we've got 10 red balls, 12 blue balls. Our ratio is going to be 10 over 12. In order to reduce that fraction, or that ratio, all we need to do is divide the top and the bottom by 2 to give us 5 over 6. Now, what is the ratio of red balls to the total number of balls? Again, the number of red balls is 10, and if we add 10 plus 12, we get 22 total balls. 10 over 22 is the ratio of red to total. Reduce it again by dividing the top and the bottom by 2, which gets us 5 over 11. Finally, what is the ratio of blue to total? We have 12 blue balls and 22 total balls. When we reduce that fraction, divide both the top and the bottom by 2, we get 6 over 11. Now let's go ahead and try a test question. Number 6 says a laboratory has 55 rabbits, some white and the rest brown. Which of the following could be the ratio of white rabbits to brown rabbits in the lab? Now, in this example, we don't have any ratios. We don't know what is the relationship of white rabbits to brown rabbits, or what's the relationship to brown rabbits and total rabbits. We do have an actual value. We know that in total there are 55 rabbits. When we look at the answer choices, we see white rabbits to brown rabbits. When we add those two values together, we get the lowest possible total number of rabbits. In order for an answer to be the correct answer, that total value must be a factor of 55, because we need to be able to multiply it by some factor in order to get 55 total rabbits. Let's try the first example. Answer choice A gives us a ratio of 1 to 3. When we add 1 and 3, we get 4, which is not a factor of 55. There's no integer that we could multiply 4 by in order to get 55 total rabbits. Eliminate A. Answer choice B gives us the ratio of 3 and 8. When you add 3 and 8 together, that tells us that at minimum, we're going to have 11 total rabbits. Now, 11 is a factor of 55. We could multiply 11 by 5 to get 55 total rabbits. That's our correct answer. The next topic that we're going to move on to is percents, because percents are actually a special type of ratio in which the total is always going to be 100. The way that we denote percents are by a symbol, and we convert percents into a fraction by taking the number over 100. Percents are going to be expressing a part over a whole. Sometimes questions will ask us to determine the percent change, in which case we're looking for the difference over the original times 100%. Notice that as with any ratio, we can write a percent in a variety of different ways. So you want to get good at converting between percents, fractions, and decimals very quickly. Let's go ahead and try an example. What is 25% of 36? The first thing that we want to do is rewrite our percent as a fraction. So take 25 and put it over the number 100. Now let's reduce that fraction. 25 over 100 is going to reduce to 1/4. Finally, we can take 1/4 and apply the percent formula. 1/4 of, which is multiplication, 36. Multiply the numerators, multiply the denominators, and you end up with 36 over 4, which reduces to 9. The next example asks us, 18 is what percent of 3? Now, before we can solve this question, we need to actually rewrite what this question is asking us to do. 18 equals what percent? That's our unknown. That's what we're going to be trying to figure out. So we'll express that phrase, what percent, as x over 100. 18 equals x over 100 of 3. That's just going to be times 3. Now we have an equation that says 18 is equal to x over 100 times 3. In order to solve for x, what we need to do is multiply both sides by 100. When we do that to the left side, we get 1800, and on the right side, the 100s will cancel out, leaving us with 3x. Our new equation is 1800 is equal to 3x. In order to solve for x, we just need to divide both sides by 3, giving us x is equal to 600. Now I'm going to give you a few moments to try percent exercises. When you're finished, we'll go through the answers and then talk about a few of these examples together. Okay, put your pencils down. Go ahead and check your answers. Now let's walk through a few of these examples together. We'll start with number 2. Number 2 asks us to convert 7 over 25 to a percent. Now what you'll notice here is that 25 is a factor of 100. That's something you're going to want to notice on test day because it's going to give you a very efficient conversion. What do we need to multiply 25 by in order to get 100? That's going to be 4. Because we multiplied the bottom by 4, we're also going to need to multiply the top by 4, giving us 28 over 100. As soon as we have it expressed as a fraction over 100, we've got our percent. 28 over 100 is equal to 28%. Now let's go ahead and take a look at number 6. Number 6 is asking us to convert a percent into a fraction. We have the fraction 16%. Now we know that 16% is equal to 16 over 100. We can reduce that by dividing both the top and the bottom by 4 to get 4 over 25. Now let's go ahead and take a look at example 12. Number 12 asks us to calculate 75% of 16. The first step is going to be to convert that percent into a fraction. So 75 over 100. Of 16 translates into times 16. Now looking at this calculation, it's going to be difficult to multiply 75 times 16, so we're going to want to reduce that fraction into something more manageable. 75 over 100 reduces to 3 over 4. Now we have 3/4 times 16, which gives us 12. Now let's move on to a test question. Number 16 says, an item is priced at 20% more than its wholesale cost. If the wholesale cost was $800, what's the price of the item? Well, if we started off with a cost of $800, we're going to need to figure out what 20% more is going to be in order to figure out the new cost. So our equation is 20% of 800. The first step is to convert 20% to a fraction, 20 over 100, and then translate the rest of that expression. Of 800 is times 800. In order to reduce this expression, cancel your zeros. Cancel the 2 zeros on the bottom with the 2 zeros in 800, leaving you with the calculation of 20 times 8, which is 160, to give us a new price of $960, which matches up with answer choice B. The next topic that we're going to cover is averages and statistics. The average formula is a very important one to remember. In order to calculate an average, you're going to take the sum of the values and divide it by the number of values. You're going to want to think of the average as the balanced value of a set of numbers. You're going to see a couple of other terms in test questions that will ask you to identify certain characteristics in a set of numbers. One of those terms is the median. The median is going to be the middle number in a set of numbers. Another term that you might see on test day is mode. The mode is going to refer to the number in a set that occurs most frequently. Remember that there could be more than one mode for a set of numbers. The range is going to be the positive difference between the largest and smallest terms in a set of numbers. Finally, standard deviation is going to be the number that represents how spread out a set of numbers is. The larger the standard deviation, the more spread apart the numbers in the set. Let's take a look at an example of an average question. Example 1 says, the average of 3, 4, 5, and x is 5. What is x? First, let's apply the average formula. Set up those values, 3 plus 4 plus 5 plus x, and then divide them by the number of values, In this case, we've got 4, so divided by 4. Then set it equal to 5. Now that we have applied the average formula, all we need to do is simplify and solve for x. So go ahead and add the common terms in your numerator, 3 plus 4 plus 5, which gives you 12. In our numerator, we now have 12 plus x divided by 4 is equal to 5. In order to solve for x, multiply both sides by 4. On the left-hand side, your 4's will cancel. On your right-hand side, 5 times 4 is equal to 20. Now, in order to solve for x, we need to isolate x by subtracting 12 from both sides. X is going to be equal to 8. An alternate approach is to think about the difference between each one of your terms and the average in order to determine what the unknown value needs to be to balance the difference. What is the difference between 3 and 5? It's 2. The difference between 4 and 5 is 1, and the difference between 5 and 5 is 0. So x must be 5 plus 2 plus 1 plus 0 in order to balance the difference, which is equal to 8. Now I'm going to give you a few minutes to try average and statistic exercises. Go through these examples, and when you're finished, we'll check your answers and go through a few examples together. Okay, stop working and check your answers. Now that you've checked your answers, let's walk through example 1. The directions tell us to find the average of the set of numbers 10, 12, 16, 17, and 20. So our first step is to apply the average formula. Take all of those values and find the sum, 10 plus 12 plus 16 plus 17 plus 20. Then we're going to take that sum and divide it by the number of values, which in this case is 5. So we have 75 on the top, 5 on the bottom. All we need to do is reduce our fraction, divide both the top and the bottom by 5 to get the average of 15. The next example that we're going to take a look at is number 4. The question says, what is the value of x if the average of -4, 0, 6, and x is 8? Notice that in this list, we have a negative number. Test questions may ask you to find the average of a set of numbers that contain negative numbers. Again, we're going to apply the average formula. So take the sum of each one of those values, -4 plus 0 plus 6 plus x, and then divide it by the number of values, divided by 4. Simplify the top, we get 2 plus x divided by 4 is equal to the average of 8. In order to solve for x, again, we need to multiply by 4 in order to get rid of the fractions. When you multiply by 4, the 4's cancel on the left-hand side, leaving you with 2 plus x. And on the right-hand side, we have 8 times 4, which is equal to 32. Isolate your variable now by subtracting 2 from both sides. X is going to be equal to 30. Now let's try a test question. The average arithmetic mean of 6 numbers is 6. If 3 is subtracted from each of 4 of the numbers, what is the new average? In this example, we aren't given individual values. We're merely told that the average of these 6 values is equal to 6. So let's pick a variable to stand in for the sum of those 6 integers. Let's call it x. Now let's apply the average formula. X, which is the sum of all 6 values, divided by 6, which is the number of values, is equal to 6. Now that we have an equation, we can go ahead and solve for that sum by multiplying both sides by 6. X is going to equal 36. Now the question tells us that 3 is going to be subtracted from each of 4 numbers. We still don't know what those individual numbers are, and we don't know which numbers we're subtracting 3 from. So we need to think about this in a more general sense. If we're subtracting 3 from 4 numbers, we're essentially subtracting 3 4 times, or subtracting 12 from the sum. 36 minus 12 is 24. That's going to be our new sum. Now, we're going to divide that number by 6 because we haven't taken away any of the 6 original terms. So our new average is going to be 24 divided by 6, which is equal to 4, which matches up with answer choice D. The next topic that we're going to cover is exponents. Exponents are going to be superscript numbers that are written after a number that tell us to multiply that number by itself the number of times of the exponent. So, for example, 2 raised to the 3rd power is going to be the same as 2 times 2 times 2, or 2 times itself 3 times. Now, there are a number of rules that govern how we manipulate exponents, and these are going to come in handy when we're dealing with numbers that are too large to calculate on test day. So, for example, the first bullet point tells us that a to the b times a to the c is going to be equal to a to the b plus c. What this means is that when you have 2 numbers with the same base and you're multiplying them, you can keep the base the same and add the 2 exponents in order to simplify the expression. The next example tells us that when you're dividing 2 numbers that contain exponents, you keep the base the same and then subtract your 2 exponents in order to simplify. Our third example, a to the b raised to the c power, is for examples in which we have a number raised to a power and then that entire quantity is raised to another power. In that situation, you're going to take the same base and multiply your 2 exponents in order to simplify. Next, when you see a negative exponent, the way to convert that expression is to take 1 over the same base and raise it to the positive exponent. So for example, a to the negative b power is going to be equal to 1 over a to the b. Now there's a couple of other things that you need to keep in mind when you're dealing with exponents. If you're doing a fraction and raising that fraction to a positive exponent greater than 1, you're actually going to get a smaller value. The higher the exponent, the smaller the result. So for example, 1/2 squared is actually going to give you 1/4, smaller than the fraction that we started with. Also, you need to keep in mind that negative numbers are going to give negative and positive results depending on the property of the exponent. So for example, when a negative number is raised to an even exponent, the result is going to be positive because all of those negative signs are going to cancel out when being multiplied by each other. When a negative number is raised to an odd exponent, however, the result is going to be negative. Let's try an example. Simplify the expression x to the -2 times y to the 3 times x to the 4 divided by x to the 6th times y to the 2nd power. First thing we want to do in a situation like this is combine like terms in the numerator and the denominator. In our numerator, we have two terms that contain the same base, x. And when we multiply two quantities with the same base, we add our exponents in order to simplify. So x to the -2 times x to the 4th is going to equal x squared. That's the only like terms in the numerator, and there are no like terms that need to be combined in the denominator. So our simplified expression so far is x squared times y to the 3rd over x to the 6th times y squared. Now we can combine like terms over the fraction bars. And in order to do that, we want to subtract our exponents. Our base stays the same, so x squared divided by x to the 6th is going to be x to the -4th power, because 2 minus 6 equals -4. Similarly, y to the 3rd power over y squared is going to be equal to y to the 1st power, because 3 minus 2 is equal to 1. Finally, we can reduce to lowest terms. Because we have a negative exponent, we can reduce to y over x to the 4th power. Now let's go through a few exponent exercises. Take a few moments to go through the following exercises, and when you're finished, we'll check your answers and then walk through a few of these examples together. Okay, stop working. Go ahead and check your answer. We're going to start by reviewing question number 7. Question number 7 gives us the example 2 squared, that entire quantity raised to the 4th power. Again, we're going to want to apply our exponent rules in order to simplify this expression. In this particular case, we're going to multiply our exponents. So our base remains the same, 2 raised to the 8th power, because 2 times 4 is equal to 8. Now let's take a look at number 9. Number 9 gives us the expression 5 to the 3rd times 5 to the negative 4th. The operation here is multiplication, which means that we're going to add our exponents. Our base stays the same, so 5 to the 3rd times 5 to the negative 4th is going to be equal to 5 to the negative 1st power, because 3 plus negative 4 is equal to negative 1. Now we can further simplify that because we have a negative exponent. 5 to the 1st power is going to be the same as 1 over 5 to the 1st power, which is just 1/5. Finally, let's take a look at example 10. This expression asks us to simplify 2 to the 7th power divided by 2 to the 3rd power. Because we're dividing, we're going to subtract our exponents, leaving us with 2 to the 4th power, because 7 minus 3 is equal to 4. Now that we've tried a few exercises, let's go through a test question together. Number 11 says, if x is equal to 2, then 3 to the x plus x to the 3rd power squared is equal to what? In this example, because we know that x is equal to 2, we can plug in 2 for x in that expression, giving us the expression 3 squared plus 2 to the 3rd power squared. Now, because these numbers are relatively small, we can go ahead and evaluate each piece. 3 squared is going to be 3 times 3, which is 9. 2 to the 3rd power is going to be 2 times 2 times 2, which is 8. And then we need to take that result and square it, leaving us with 9 plus 64. Our final step is to just complete the sum. 9 plus 64 is equal to 73, which gives us answer choice E. Our next concept is radicals. There are a similar set of rules that govern the way radicals can be manipulated. So let's go ahead and take a look at those rules so that you understand how to simplify an expression that contains radicals or square roots. First example says the square root of a times b can be split up into the square root of a times the square root of b. This is a concept that is frequently used to change the way an answer choice looks so that it either matches up with what you have in your scratch paper or so that it's put into a different format in order to manipulate an expression. The next bullet point says the square root of a over b simplifies to the square root of a divided by the square root of b. Now the next two bullet points are cautionary. The square root of a plus b does not equal the square root of a plus b. You cannot pull apart a sum when it's underneath a radical sign. Similarly, square root of a minus b does not equal the square root of a minus the square root of b. The next point states that the square root of a squared is equal to a. Taking the square root of something and then squaring it basically undoes the operation. So you're just left with whatever number is underneath the radical sign. Finally, another way to state the square root of a is a raised to the 1/2 power. That's going to be a helpful trick when you're trying to simplify square roots, especially when you're dealing with a division problem. Let's take a look at an example. The first example gives us a large square root, the square root of 4 times 9 plus 9 times 16 divided by 25. If you take a look at the operations underneath the radical sign, we have two multiplication signs, an addition sign, and a division bar. Remember that we cannot split apart the sum, but we can split apart the quotient. So you can convert this expression to the square root of 4 times 9 plus 9 times 16 divided by the square root of 25. The reason that that was helpful was because the square root of 25 is a perfect square that we can simplify. Now that we've simplified the denominator to 5, let's see what we can do with that numerator. Like I said earlier, we can't split up the sum, but we can take a look at the numbers that are in common with that sum. If we take a look, our first term is 4 times 9, our second term is 9 times 16. Both of those terms have a 4 in common as well as a 9. So we can pull out a factor of 36 and see what we have left over. Pulling 36 outside of the parentheses leaves us with 36 times 1 for the first term plus 4 for the second term. Simplify what you have inside the parentheses and we have the square root of 36 times 5. Now that we have re-expressed that expression as a product, we can now split apart our square root, leaving us with the square root of 36 times the square root of 5 over 5. We have one last step. Simplify the square root of 36. 36 is a perfect square, which means that the square root of 36 is 6. Final answer is 6 times the square root of 5 over 5. Now let's take a look at our second example. We're given the square root of 12 raised to the 4th power. The best way to simplify this example is to rewrite the radical as an exponent as explained in the last bullet point. Rewriting the square root of 12 to the 4th power as an exponent, we now have 12 raised to the 1/2 power, and then that entire quantity raised to the 4th power. In order to simplify, all we need to do is multiply those two exponents, 4 times 1/2, and keep the base the same, giving us 12 to the 2nd power, or 144. Now let's go ahead and take a look at those radical exercises. Take a few moments, go through each exercise, and when you're finished, we'll check your answers and then review a few questions together. Okay, stop working. Now go ahead and check your answers. Okay, let's start by walking through number 1 together. Number 1 asks us to solve the following problem, the square root of 2 times the square root of 8. On test day, you want to look at these square roots and ask yourself, is this something that I can easily calculate in my head? If not, then you're going to want to look to apply a rule in order to simplify the expression. So in this case, the square root of 2 and the square root of 8, neither of those are perfect squares. So we're going to want to manipulate them in some way in order to simplify the expression. Our first bullet point told us that the square root of 8 times the square root of 2 could be changed to the square root of its product, or the square root of 16. The square root of 16 is a perfect square, which we can evaluate to equal 4. Now let's go ahead and take a look at number 3. Number 3 asks us to solve the square root of 48 divided by the square root of 3. Again, neither of those two numbers are perfect squares. But when we combine the quotient and take the square root of 48 divided by 3, 48 divided by 3 is 16, which again is a perfect square. The square root of 16 is 4. Our next example is number 6. This question asks us to take the square root of 49 minus 36. Now, it's going to be tempting to split apart that difference because both 49 and 36 are perfect squares. But remember our caution notes. You cannot separate a square root in which there is a subtraction problem underneath. So all we can do here is complete the subtraction problem. 49 minus 36 is 13. Correct answer here is going to be the square root of 13. It cannot be simplified any further without a calculator. Now let's take a look at example 8. This question gives us the square root of 16 in parentheses and then squares that value. Remember that when you take the square root of a value and then square it, the two operations undo each other, which means that we basically end up with 16. Another way to explain that would be to rewrite the square root as an exponent. The square root of 16 is equal to the same thing as 16 to the 1/2 power. When we take 16 to the 1/2 power and then square it, we multiply those two exponents. 2 times 1/2 is going to be equal to 1, which means that our answer is 16 to the 1st power, or 16. Now let's go ahead and move to a test question. Number 11 states that if x is greater than 0 and y is greater than 0, which of the following is equal to y divided by x times the square root of x to the 3rd power over y? Now, in order to simplify this expression, we're going to need to convert that radical symbol into an exponent. So keep your first term the same, y divided by x, but now multiply it by a term raised to the 1/2 exponent. So x to the 3rd divided by y raised to the 1/2 power. Now we're going to need to apply that exponent to both of the terms in our quotient. So again, your first term is going to stay the same, y over x. Multiplied by x, this time we're going to multiply 3 times 1/2 to give us 3 over 2. And then multiply 1 by 1/2 to give us y to the 1/2. Now let's go ahead and multiply that out and put it into a format that's going to make it easy to apply another exponent rule. On the top, we have x raised to the 3/2 power times y raised to the 1st power. In the denominator, we have x to the 1st power and y to the 1/2 power. Now that we have our like terms lined up, we can combine over the division bar. X to the 3/2 divided by x to the first is going to be x to the 1/2 power, because 3/2 minus 1 is equal to 1/2. Next, y to the first power divided by y to the 1/2 power is going to be equal to y to the 1/2 power, because 1 minus 1/2 is equal to 1/2. So now we have our answer, x to the 1/2 power times y to the 1/2 power. Now take a look at your answer choices. None of those answer choices look quite like that, so we're going to need to convert those exponents back to square roots. X to the 1/2 is the square root of x. Y to the 1/2 is the square root of y. So we have the square root of x times the square root of y, or the square root of x times y, which matches up with answer choice D. Now we're going to cover order of operations. PEMDAS, the acronym for remembering the order of operations, governs the order in which you're going to add, subtract, multiply, or divide in any given equation. The P in PEMDAS stands for parentheses, the E stands for exponents, the M stands for multiplication, the D, division, A, addition, and S, subtraction. You might want to remember the phrase, "Please excuse my dear Aunt Sally." This mnemonic is going to help you remember the order of operations. Also, keep in mind, if your expression has nested parentheses, you're going to want to work from the inner set of parentheses outward. Now, when you're looking at the order of operations, you'll notice that multiplication and division come first before addition and subtraction. When you see parentheses in an equation, they've often been put there in order to write an exception to this rule, in order to force you to do addition or subtraction before the multiplication and division. So watch out for those parentheses. Now let's take a look at an example. We have the expression 30 minus 5 times 4 plus parentheses 7 minus 3 squared divided by 8. Let's start by evaluating the parentheses. There's a subtraction problem inside the parentheses, so we want to take 7 minus 3, which is equal to 4. Now, when we rewrite our expression, we want to replace 7 minus 3 with the value of 4, but then copy everything else down as accurately as possible. So our new expression is going to read 30 minus 5 times 4 plus 4 squared divided by 8. Let's tackle the exponents next. 4 squared is equal to 16. So again, we're going to substitute out 4 squared and put in the value of 16, giving us the expression 30 minus 5 times 4 plus 16 divided by 8. Our next task is to take a look at the multiplication in the expression. We have 5 times 4 in our expression, which is equal to 20. Replacing that, we get 30 minus 20 plus 16 divided by 8. Next, we want to tackle division. 16 divided by 8 is equal to 2, leaving us with the expression of 30 minus 20 plus 2. Our addition problem comes next. We want to add negative 20 plus 2. Remember to preserve the negative signs when you're adding so that you make sure to get an accurate answer. Negative 20 plus 2 is equal to negative 18, leaving us with 30 minus 18. The final step is to perform the subtraction problem. 30 minus 18 is equal to 12. Now I'm going to give you a chance to try a few order of operation exercises on your own. Go through the following exercises, and when you're finished, you'll check your answers and we'll walk through a few exercises together. Okay, now that you're finished, check your answers. Good. Now that you're finished looking at the answers, let's go through number 1 together. Number 1 gives us a long expression, and we're going to need to use order of operations in order to simplify. We have 7 plus 5 times 1/4 squared minus 6 divided by the quantity of 2 minus 3. We want to start with our parentheses first. Inside the parentheses, we have 2 minus 3, which is equal to -1. Let's replace 2 minus 3 with that value of -1, giving us the expression 7 plus 5 times 1/4 squared minus 6 divided by -1. Don't forget the negative signs, because otherwise you're going to end up with a different result. Now let's tackle the exponents. 1/4 squared is going to be equal to 1 over 16. When you square a fraction, you merely square the top and square the bottom. Now let's replace that, giving us the expression 7 plus 5 times 1 over 16 minus 6 divided by -1. Multiplication comes next. 5 times 1 over 16 gives us 5 over 16. Replacing that in the original expression gets us 7 plus 5 over 16 minus 6 divided by -1. Division comes next. -6 divided by -1 is going to give us a value of 6. Remember, when we divide two negative numbers, our negative signs cancel out. Replace that value in our original expression, giving us 7 plus 5 over 16 plus 6. Now, as you can see, the only operation left is addition. Addition is commutative, which means that we can do it in any order we want. In this case, let's add the whole numbers first. 7 plus 6 is equal to 13, and we can express the correct answer as 13 and 5/16. That wraps up our arithmetic lesson. You've learned everything that you need to know in order to be successful on the arithmetic portion of the test. Congratulations! Now, remember to practice the concepts that you've learned today so that you can apply these concepts efficiently and effectively on test day.